topics in terms of data, so this is why we decided to include this, right? Let me just give you an idea of this. So this is the answer that you get for the upper and lower bound. The proof uses, now we have to take care of the infinite extensions of these guys. Okay, this is the work of Jeff Lawler in 1981, and you have to analyze the asymptotics carefully. So this is the picture. So this is what it should be in black. This is the upper and lower bound. What had been done just for beta, half the naturals, now it's done for all real beta. And now let me just show you briefly the solution. How would be the solution of these problems in general? Again, now I start with this measure here. du 1 minus sin pi x squared over pi x squared. What's the goal? I know how to solve this sort of problems if I give you the Brownian spaces, the Brownian space. So I have to find the Brownian space E, that is the right Brownian space for this measure, such that the E of x to the minus 2dx is not equal pointwise to this, but such that for all functions in the space, the magical identity will hold. Let's see. Suppose I want to solve the delta problem here, like the one delta problem that I mentioned here before and the two delta problem that I mentioned again. So the one delta problem is non-negative function such that r of 0 is bigger than 1. The two delta problem is non-negative function such that r of plus or minus beta is bigger or equal than 1. You want to minimize this L1 norm with respect to the correlation measure. The idea here is to consider the space, non-considering PW of pi nu, the class of entire functions of exponential type at most pi, such that this norm, now the L2 norm against the d mu of x is finite. Right? And of course you write PW of pi as the linear space question, right? So you have the measure 1 over 1 minus sin pi x over pi squared, and you have the Lebesgue measure. First problem is that I claim to you that these two spaces are the same as sets, and the two norms are equivalent. Right? Why are the two norms equivalent? Of course, if you take the norm with 1 minus something, you get less than the Lebesgue measure. Right? So one inequality is trivial. And the other inequality, why is this norm with the 1 minus something? Because it has a singularity at the origin. Why does it still control the L2 norm? This is because of the uncertainty principle. Because of the singularity at the origin, the mass cannot be too concentrated at the origin, because the function has a complex Fourier transform. So a part of the mass should be outside of the origin, and if 70% of the mass is outside of the origin, the two measures there are comparable. So you have that the two spaces are equal sets and the norms are equivalent. Which is great, because you know that the linear space is a space where the functionals, the evaluation functionals are continuous. Now, if the evaluation functions are continuous in one space and the two norms are equivalent, the evaluation functionals are continuous in the other space too. So the function that takes a function to a point, to a value f of w is continuous on my space that I call h here. H is my linear with the fair correlation measure. Well, but if the evaluation functionals are continuous, it means that there's just a magic reproducing kernel, such that f of w is equal to the inner product of f against this guy on this space. But this is the inner product. And the question is, who is this reproducing kernel in this magic fair correlation space? And here's the answer. This is the fair correlation, this is the reproducing kernel for the Hilbert space with the fair correlation measure. Now, if you have the reproducing kernel of the space, it is very easy to solve the one delta problem, as we saw on the first slide. To solve the one delta problem is the very same solution using Cauchy-Schwarz that we did. And the answer is, again, you have to have a multiple of the reproducing kernel and the best solution. To solve the one delta problem. The solution of the two delta problem, to linearize plus and minus delta, to linearize d1 as plus and minus delta, also falls into a general problem in Hilbert space. So you have to solve this general problem in Hilbert space. If I give you a Hilbert space over C, and I give you two non-zero vectors v1 and v2 with the same norm, I consider the set J of vectors x such that x scalar v1 is bigger than 1 in absolute value and x scalar v2 is bigger than 1 in absolute value. Find the minimal value of an element in this space. I give you two spaces, I want to make this condition hold. And then, well, this is a basic problem in geometry of Hilbert space. You work with it, you can find the answer. The answer is this. And this gives us the solution of our two delta problem. I want to talk about, we can actually solve the problem of regularizing and minorizing characteristic function of the interval with respect to this measure. The solution is rather complicated, but the bottom line is that the difference between the major and the minor is exactly this guy. Note that when vector is not an integer, when vector is half an integer, this guy is not here. So the only thing that we have to solve is this thing, but this should be here. A little picture of this is given by this guy. So the difference between the upper and lower bound is less than this. So whenever beta is small, say our upper and lower bound are relatively close. Of course, the upper and lower bound is always, the difference between the upper and lower bound is always less than 1. But here is considerably less than 1. Well, just to finish, I told you that I was going to give you the Brownian space such that this magic identity happens. For all functions, there is a space E such that r of x e to the x minus 2 is equal to this fair correlation measure, and that the Brownian space is given by this guy. So you start with the big K that I showed you on the previous slide. You construct this function L of w z 2 pi I w1 minus z times k, and this E of z is L of I z over L of I by half. This is contained in problems 49 to 53 of the Brownian book. But if you have never seen this, the Brownian book is a very unique book, at least in my opinion, because I mentioned the problems by heart because the problems in the book are part of the theory. And in order to move to the next session, you have to have solved all the problems before. Because you leave part of the theory in the problems. So they go to section 4 and say, my problem blah, this happens, my problem blah, this happens. And you're screwed if you're not solve the problem. This was very hard to me when I was a grad student. I think I gave up on page 3. I started studying page 3 with that. This is too hard. And then I decided I gave another try. And in the last semester I would say, hey, I have to learn this thing. And the best thing to learn something is actually propose a course. So I proposed a topics class, and we got together with a very nice group of students. And we pretty much covered like half of the branch book, the big book. We know that exercise. These guys did much better than I did when I was at their age. There is a fun story. So, of course, in the beginning, few of them were finding it very hard, the book to follow. And without my knowledge, one of them had the idea to write to the branch himself. So we wrote an email, found the email of Professor Louis DeBranche online, and said, Dear Professor Louis DeBranche, I am a student here in INPA, and we are taking a very nice class in your book. It's a very nice book, but very hard to follow. I wonder if you had additional lecture notes on this, I could follow, blah, 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 best regards, blah, blah, blah. Professor DeBranche replied in one day, and the answer was like this. Dear blah, 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 you were right about one thing. My book is indeed a great contribution to analysis. You should see my proof of the Riemann hypothesis, blah, blah, blah. And he goes on about 15, 20 lines of blah, blah, blah. I think I'm correct, right? Then I can tell the story about these guys. So he's a character. I had never had the chance to meet him in person, but I really admire his work. I know that these sort of human spaces are very, very interesting. They're very magic. And, well, with this, I want to finish my talk, just making you an invitation. As you know, in a couple of weeks, in 2 weeks, when the ICM starts, I'm going from here to Korea, we'll be presenting a bid to host the ICM in 2018 in Rio de Janeiro. We are very confident that our bid will be accepted. Well, I have to make sure that Germany is not competing. But if Germany is not on the run, I am confident that we have a good chance. And if this indeed materializes, you are all invited for the ICM in Rio in 2018. And thank you very much for your attention.
Opportunity to speak here. I'm especially pleased to be able to speak in the city in which Hausdorff worked for much of his career. So just to fix some very standard notations, the LP norm of a function will be written as f with the subscript p. I'll almost always be integrating with respect to Lebesgue measure. P with the absolute value signs will denote the Lebesgue measure of a set, and occasionally, just in some digressions, the cardinality of a finite set, but almost always the Lebesgue measure of a subset of Euclidean space. This notation is the indicator function of E, is 1 on E and 0 on the complement of E, and I'll be talking about the Euclidean Fourier transform normalized as follows. So x is a point in Rd, c is a point in the dual group Rd, f out of c is the integral of e to the minus 2 pi I inner product of x with c, f of x dx. Okay, and part of my slide seems to be missing. Okay, so this is, I'm afraid that part of all the slides will be missing. We'll see what happens. The Hausdorff-Young inequality is one of the very most basic inequalities of linear analysis. So first of all, on L2 of Rd, the Fourier transform is unitary, preserves norms. It's a contraction from L1 to L infinity. And for intermediate exponents p, if p is between 1 and 2, the Hausdorff-Young inequality says that the Fourier transform is of an LP function. The Fourier transform is in LQ, where Q is the conjugate exponent, and there's an inequality of the LQ norm of f is less than or equal to 1 times the LP norm of f. So this was proved by Young in 1913 in the special case of even integer exponents. Q is 4, 6, 8, 10. And this is a common thing in the subject. There are many theorems that have been proved first for even integer exponents, and perhaps later for general exponents. And this is one case. 10 years later, Hausdorff proved the inequality for the full range. Those were very primitive days, and if you know about interpolation, which is the method we would use nowadays to prove this in half a sentence, interpolation was simply not known back then, and Hausdorff really did not interpolate in any sense. He had a more involved argument. Okay, this inequality properly formulated works on any locally compact abelian group with a constant of 1 in the inequality, and that constant is optimal for many groups, and for many important groups, it's optimal for a torus, and it's optimal for the integers of any dimension. Okay, so my talk is about a short version of this inequality. The short version gives the optimal constant. So the norm of f hat in L2 is less than or equal to a certain constant a. A depends on the exponents. It's raised to the dimension d. A sub p to the d times the LP norm of f. And the optimal constant is, the AP, the optimal constant in dimension 1, is p to the 1 over p divided by q to the 1 over 2p divided by q to the 1 over 2q, where p and q are the two exponents in the inequality. This was first proved by Babenko, again, for even integer exponents, by a proof which is not the one we use. And in this talk, the Gaussian will always mean a complex constant times an exponential. The exponent is a quadratic polynomial. The second degree part of the exponent is negative, definite, and real. And the coefficient of x is allowed to be complex. So that's what a Gaussian will be. Becker's proof shows that these functions extremize the inequality. That still left the question of whether there were other extremizers, and that was solved by Lieb in 1990. So Lieb showed that there are no other extremizers. All the extremizers are exactly the Gaussians. And along the way, he gave a completely different proof of Becker's theorem, whereas Becker's proof was really very much a proof in hard analysis. Lieb's proof was a proof by symmetry. He exploited very heavily the connection between the Fourier transform in R1 and the Fourier transform in R2. If you have a product of two functions, a product function in R2 is Fourier transform is just a product of two one-dimensional Fourier transforms and things of that type. He used the rotation symmetry of the inequality, and altogether a very clever argument. So this identified the extremizers. Okay. Now this slide is just an example, but it's a very fundamental example. We all know that the Fourier transform is a non-local operator, and I just want to show some examples of how that actually plays out for this question of what the extremizers are for the inequality. So here we have the following kind of example. We take the integers 1, 2, etc., 3, up to some n, and this is a picture in one dimension. And about each of these, we put a little interval. The intervals are all of the same length, and they have a length which is 1 over some other capital M. And my function f is just the indicator function of the set E, so E is just a union of all these intervals. Okay, so E is a set of some measure, and what we want to do is we want to feed this set E into this ratio. And the fact is that if you let M or N or both go to infinity, this is bound to be low uniformly for all M and N. So the interesting case is where they converge. I'm not saying that those functions extremize the inequality, but they don't do a bad job. They come within a very reasonable fixed factor, no matter how large M and N are. So this is a very strong kind of non-locality. There are competitors in this problem, competitors that try to extremize, that do pretty well and look nothing like Gaussians. Okay, and that will be fundamental throughout the discussion. Okay, in my talk there's only one theorem, and the talk will mostly be about an outline of the ideas in the proof. And here's one version of the one theorem. So given a dimension, there's a positive constant C, so for any function f in LP, the L2 norm of f is less than or equal to the optimal constant times the norm of f minus something concrete. So this says, of course, that the concrete thing involves the distance from f to the set of all Gaussians. This function G is supposed to use Gaussians. This says in particular that only Gaussians can extremize, but it gives you a quantitative form of that statement. It tells you that you miss extremizing by a definite amount if you're a definite distance away from the Gaussians. Okay. Now, the exponent 2 here is, of course, optimal. If you have a function which has a maximum, then if there's any justice in the world, there are some directions in which you perturb and it varies quadratically. So this is the best you could hope to have. But one can try to get one's hands on this other constant here. So here's a more refined version. So that f is very close to the Gaussians in the sense that the ratio of the distance to the norm of f is very small. Then there's a more concrete second term with an explicit constant here, which is half p minus 1 times 2 minus p times the optimal constant in the inequality. And then there's a little other term, which is a little smaller than quadratic. Okay, so there's a concrete statement. And you probably want me to say that this constant v is optimal, but it's not. There's a third version of the theorem which I'm going to spare you. The statement is longer and less pleasing. But in that third version, the distance is measured in a slightly different way. And in that third version, this constant v here actually appears, and it is an optimal constant. So in a sense, there is an optimal constant for this next term in the inequality. But you have to formulate it just right, and it's a little awkward. Okay. Now, I'm going to devote almost the entire lecture to outlining the proof of a much weaker statement. So this is a completely non-quantitative statement. So again, function G is a set of all Gaussians, which is a certain finite dimensional subvariety of LP of RD. And the theorem says that given any epsilon, there exists a delta, so that if you come within a factor of 1 minus delta of extremizing, then you must be within distance epsilon of a Gaussian, with the appropriate homogeneity in the norm of f. Okay? Not just the statement, but the proof itself gives absolutely no information about the dependence of delta on epsilon. There's a compactness step which loses all information. Okay. So in fact, this is the main step. Even though I'm aiming for a very precise theorem, the main step is this very imprecise one. Okay. This really is a compactness statement of the following type. Suppose you have a sequence of functions fn, whose norms approach 1, so that the norm of the Fourier transform the precise statement here is that if you act on each function by an appropriate element of the symmetry group, which I'll explain in a minute, then you got a set which is precompact and has a convergent subsequence. Okay. Now the theorem I stated in the last slide said that you have to be close to, if you nearly extremize, you're close to a Gaussian. What this version proves is that extremizers exist, and if you nearly extremize, then you're close to an extremizer. So Leib identified the extremizers as Gaussians, and the theorem F1 that I stated is a combination of the compactness statement and the theorem of Leib. Okay, so the theorem of Leib is very much a part of the story here. Okay, so the proof of the theorem goes like this. There are really three parts. There's this compactness statement, which shows that near extremizers, after renormalization by symmetries, form a precompact set. That lets you take limits. When it goes to Leib's theorem to identify the limits as Gaussians, and then there's a third step, which is completely different in technique. Once you know you're very close to an extremizer, you can take the functional norm of F hat over norm of F t. You know F is very close to a Gaussian, and you expand this in Taylor series about a Gaussian, and you just analyze the quadratic part of that Taylor expansion. So that's rather algebraic. I'll talk a little bit about that at the end, but that's not the main point. So that's how one goes from a completely non-quantitative statement to a rather precise one. It's because at the end you can do a completely different analysis once you know you're close to a Gaussian. Okay. All right. So the inequality has a number of symmetries of various kinds, and a very important one is you can compose a function with any element of the general linear group, and the ratio of the norms is completely preserved. Okay. We're accustomed in analysis to seeing inequalities that are invariant under translation, maybe rotation, often dilation. It's rather rare to have the full affine group as a group of symmetries, but one has it here. Okay. One has translations. One has modulation. One can multiply F by an arbitrary unitary character. And of course one can multiply by scalars. So as a result, there's a big group of symmetries. It's certainly a non-compact group, and that has to be taken into account in any sort of precompactness argument. Okay. The presence of the affine group as a group of symmetries, of course, strongly suggests some of the things that might arise in the analysis, namely things that are invariant in our affine transformation. So, of course, the class of convex sets is affine invariant, the class of ellipsoids is affine invariant, and, of course, we expect to see ellipsoids, those are super-level sets of Gaussians. And, of course, well, that suggests what you might see, but there are other things that are invariant under affine transformations as well. Those are what I call continuum multiprogressions. So first of all, discrete multiprogression is a well-known kind of object. So it's a set Q. It has a starting point U. There are finite limiting steps, d sub I, and you're allowed to step a certain prescribed number of times in each direction, d sub I. And all sums you can get to in that way with a certain number of steps in each direction. That's a multiprogression. All right, so here I gave you, well, let me come to this in a second. What we're going to be working with are continuum multiprogressions. They are sums of discrete multiprogressions and ellipsoids, or if you prefer, convex sets, either one. And those are equivalent definitions for my purposes. So a continuum multiprogression is the sum, all the points you can get by adding elements of a discrete progression to a convex set. So in one dimension, the convex set of the ellipsoid is just an interval, and here we have a typical example of a continuum multiprogression. Here's the discrete part, and then this is the continuum part. Okay, and of course those are invariant under affine transformations. Okay. An important concept in the proof would be quasi-extremizers. So if you have a number of delta, which typically would be very small, a delta quasi-extremizers of an inequality like this is a function f for which the norm of t of f is greater than or equal to delta times the optimal constant times the norm of f. So we're mainly going to be interested in the case where delta is very close to 1, but the proof has to use the case where delta is very small. So those are quasi-extremizers. And for many inequalities, it's interesting to study quasi-extremizers. It's a rare inequality for which you expect to be able to find optimal constants and extremizers exactly, but quasi-extremizers are more robust. They tell you a lot about the inequality, and that's something that's interesting to characterize. One expects to be able to do that more often than actually finding extremizers. Okay, we're going to explore the connection with Young's convolution inequality, and indeed, Hausdorff's original proof of the Hausdorff-Young inequality is this. He used the fact that a square is the Fourier transform of a convolution, and he used Poincaré theorem, he used other known cases of the inequality, and he was able to reduce the facts about convolution that had been proved by Young. So Young's convolution inequality, I specialize the exponents a little, says that a certain LR norm of a convolution of two functions is less than or equal to a constant times the LS and the product of the LS norms if R and S are related by a certain scaling relation. Okay. The optimal constants in this inequality are known, the extremizers are known. One knows that the only way to nearly extremize the inequality is to be near extremizer. So this is something that's already well understood from the point of view of today's talk. So this lemma, if you have a delta, and if F is a delta quasi-extremizer for the Hausdorff-Young inequality, then it's also a delta quasi-extreme, then a power of F is a delta quasi-extremizer for Young's inequality with appropriate exponents. You have to change delta to delta squared, but that's so important for me. Okay. So the point here is that quasi-extremizers of one inequality are closely related to quasi-extremizers of the other. And that will allow us to extract information about the Fourier transform inequality from information about the convolution inequality. The convolution inequality should be much easier because there's no cancellation. So this is a quick answer. So that's a more elementary kind of inequality. Okay. Now, sharp constants for the two inequalities are not connected in this way. There are certain cases where you can go from one to the other, but for the full range of exponents, it's not the case that you can connect extremizer or extremizer to one in a simple way. Okay. Young's inequality is really about sum sets, and this is where the additive combinatorics starts to come in. So the sum of two sets, A and B, is just a set of all pairwise sums, little a plus little b, where little a and little b are drawn from the two sets. And we think of non-negative functions as just being sets with weights. The function is a weight on its support. And the convolution of two functions is just a count of, it's a kind of weighted subset. The convolution of f and g at some point x is just a number of ways of writing x as an element of the support of f plus an element of the support of g, weighted by the weights f and the weights g. So you weight each pair by the product of the value of f and the value of g. Okay, so it's reasonable to expect that some sets may appear in our discussion of at least for Young's inequality, and therefore they should be around the discussion of Hausdorff-Young. Okay. Now, I told you that it was going to be important to understand quasi-extreme isomorphisms for the Hausdorff-Young inequality, and I said they were related to quasi-extreme isomorphisms for Young's inequality. So here we characterize quasi-extreme isomorphisms for Young's inequality. So suppose that F is a delta quasi-extreme isomorphism in this sense, then